Very good morning to everybody. Welcome to the 8th session of classical mechanics. In the last session, we have discussed the applications of Lagrangian equations for some of the constrained motions. In continuation, let's discuss some more applications of Lagrangian equations. The Lagrangian equation of a motion is given by d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to Qi, which is a general form of Lagrangian equation. For a conservative force, Qi is equal to 0. Then the Lagrangian equation of a motion reduces to d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to 0. So the objectives of these sessions is to understand the applications of Lagrangian equations for a constrained motion. By the end of this session, we will be able to understand how Lagrangian equations are applied for a particle in a free space and a freely falling body. Problem number 1. Motion of a single particle in Cartesian coordinate system. A single particle in a free space has 3 degrees of freedom. Let x, y, z be the Cartesian coordinates of the particle. Then the velocity of the particle of mass m along x, y, z axis will be x dot, y dot and z dot. We know that for a conservative system, the Lagrangian equation is given by d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to 0. Let x, y and z be the independent coordinates. Then d by dt of dou L by dou x dot minus dou L by dou x is equal to fx. Likewise, d by dt of dou L by dou y dot minus dou L by dou y is equal to fy. And d by dt of dou L by dou z dot minus dou L by dou z is equal to fz. Where fx, fy and fz are the components of force along x, y and z direction. Differentiating L term with respect to x dot, it reduces to mx dot. And differentiating L with respect to x is equal to 0. Using Lagrangian equation, d by dt of mx dot is equal to fx. On differentiation, it reduces to mx double dot is equal to fx. Likewise, for y component, the differentiation reduces to my double dot is equal to fy. And for z component, reduces to mz double dot is equal to fz. In vector form, it is given as mr double dot is equal to m of x double dot I cap plus y double dot j cap plus z double dot k cap. That is equal to force along x component I plus force along y component plus force along z component, which is equal to the total force. We observe that it is F is equal to mr double dot, which is nothing but Newton's second law of motion. Let's discuss problem 2, which is motion of a freely falling body. Consider a body of mass m is falling freely under the action of gravitational force. Let y be the Cartesian coordinates of the particle. Then its velocity is y dot along y-axis. Then the kinetic energy of a freely falling body is given by half m y dot square, whereas the potential energy is given by minus mgy. We know that Lagrangian is equal to kinetic energy minus potential energy. So the Lagrangian of a freely falling body is equal to half my dot square plus mgy. Differentiating Lagrangian term with respect to y dot, we get my dot. Likewise, differentiating L with respect to y, it reduces to m into g. Substituting dou L by dou y dot and differentiating further with respect to t reduces to my double dot, and dou L by dou y is mg, or the equation is given by y double dot is equal to g, which is the required equation of a motion for a freely falling body under the action of gravitation. So in this session, we have learned the application of Lagrangian equations for a single particle in a free space and for a freely falling body. Hope you enjoyed. Thank you all. For the references, Classical Mechanics by Goldstein, Classical Mechanics by Gupta, Kumar and Sharma, Classical Mechanics by Takwala and Puranik, Classical Mechanics by J.C. Upadhyay. Thank you.